इसी से चलेगा ना? ओके, इसमें एस्केप भी है इधर, ये भी चलता है, ठीक है, ओके. So very good morning to all of you, and thanks to Arun Kumar from Pune, and Parag ji and Jyotsna ji from all from CWPRS Pune, and he has very rightly pointed out that Atmanirbhar Bharat हम लोग को मिलकर करना है. पता नहीं अभी ये क्या मतलब हम आज दोनों हैं. मेरा नाम भी एक्चुअली अरूप कुमार ही है पासपोर्ट में, शर्मा बाद में आते हैं, और ये है अरुण कुमार. कलर भी एक जैसा हो गया है आज, पता नहीं क्यों. सो हमको ये बहुत अच्छा लगा कि आज टुडे वी आर मीटिंग हियर टुगेदर. एक्चुअली वी हैव गॉट लॉट ऑफ support in the sense that okay, this should be improved that way from CWPRS in Brahma model from long back, and they are also running it there. That way it is we need to work together to make Atmanirbhar with the Brahma's Asirvad. Okay, so with that very introduction, let me move to the why actually we need our indigenous model. Okay, so because of high population, unlike Western world, in India, our habitation exists near all different reaches of the river, whether it is bouldery river or what kind of river. In hilly internal we have people. Therefore, for a country like India, we come across and witness many flow phenomenon. Like that we are now facing so much of flash flood kind of things. Whether we can exactly call that as a flash flood depending on the definition, that's a different point, but it is basically the water rushing down and then getting a shallow channel because of the sedimentation and then flooding. So that kind of things we are also working on. And so many other phenomena are also there, like one very interesting phenomenon called Hamal in river Brahmaputra. In braided river we observe that when sometimes the water flow and it stops for sometimes and then again it moves. So velocity become almost zero and then it again moves. So it is because of confluence of two channels. When this channel become higher, then this water stop and then accumulation of water happen, head increase, then it push again. Then this will stop. So that kind of phenomena are also there in confluence. So we are also working on that kind of situation. So I mean just an example why the different kind of phenomenon we come across. And the model, to model those phenomena, we need to do in-depth study of the actual process and should not use model as a naive user. I mean, in modeling there are, suppose naive user means who can just run the model, some people who understand the internal things. So we should not limit ourselves in the naive user, rather we should go for the internal process understanding, and that way we should develop what the equation is there, and those things are important. And coupling of different models. When you have your own model, then coupling of different modeling components representing different processes related with hydrology and river flow is extremely important. For example, when we are having Brahma model, so for example coupling reservoir operation model, that's a completely different model, but we can couple a reservoir operation model with our hydrodynamic model, because based on reservoir operation we will be knowing how much water you are releasing to the downstream, and from that Brahma model can simulate at the downstream what flow can be there. So that kind of model also we have developed. Similarly, coupling of confluence modeling with aquatic behavior, like say for various aquatic life, fish, or which are, fish is directly related to us, but various aquatic other vegetations are also important. So those things, understanding how they will behave or how they will grow or whether they will grow or not, all those things can be understood by ecological modeling. But then for that we need again the characteristic of flow. For that we can do hydrodynamic modeling. So the Brahma model can be coupled with those also. Analyzing impact of vegetation on the flow, characteristics. So we are now talking about nature-based solution for erosion control in many places. So there, if we put a vegetation, how it will work how the vegetation characteristic, depending on the vegetation pattern, how the velocity will change, all those things can be done. Similarly, I mean, coupling of optimization model with river flow simulation. Suppose we are talking about river flow simulation and we are talking about river training work. Then we generally take that, okay, this many spars will be good, or will resist this part. But now there remain question that what should be the length of spar, what should be the spacing between the spars. Just an example I am talking about. So for a particular area which will be most optimal conditions of the spar length and spacing, which will reduce the erosion or which will reduce the velocity to the required level at minimum cost. So that way we have coupled Brahma model with that kind of optimization model as well to decide the most optimal combination of this kind of things. We can do that. So similarly, groundwater infiltration in 1D model, we can do that. If the flow is coming, then what is the groundwater infiltration? Because in particularly in northeastern part, on Ganga also we have seen there are some piedmont zone where a lot of water infiltrate into the ground, and then suppose sometimes you find that upstream water is more than the downstream water. It becomes confusing why the downstream water is getting reduced, because a lot of water is infiltrating zone. Geologically it is called piedmont zone, which is highly permeable. Lot of water is infiltrating into the ground. Then again it will meet at the downstream. So we coupled this surface water as well as groundwater flow movement. That kind of things can also be done when you have your own modeling tools or modeling setup. So Brahma model includes simulation of vegetation, simulation of porcupine, simulating impact of breeze. I mean, these are common, simulating morphological change, that how sediment change and so on. So there are several options. So most importantly, India should have its own river modeling software rather than remaining dependent, fully dependent on model developed by other countries, because geopolitical situation, we were just discussing, geopolitical situation also keep on changing. Like US now we are getting freely HEC-Ras, but mic is highly priced, of course, DELF. So if we have our own model, we can have our own stand. So these are some of the points that I just wanted to highlight before going to the actual model. And as this course is mostly covered by covered on HEC-Ras, unsteady flow modeling, I'll just briefly show you some of the things of HEC-Ras, because we have also used HEC-Ras extensively earlier. That its version 1 first released in 1995, marking the start of the software. Then different versions are coming. As you can see that why I am presenting this point, things always keep on improving, whether it is HEC-Ras, mic, Brahma, things is always, improvement is always a continuous process. Say in 1997 added unsteady flow capability, in 2000 sediment transport model came in HEC-Ras, then 2008 to 2010 added initial two-dimensional model, but that was not that good at that time. And in 2016 they have enhanced their 2D model. So that way different versions, different things keeps on coming. So this is about the HEC-Ras, how it is, history of HEC-Ras, how it is developing. And then what kind of equation, the governing equation when there is 1D model, then this is basically continuity and momentum equation which is being used, okay, very common equation, and they are using implicit finite difference scheme at that time. Then governing equation in 2D, that is again basically continuity and momentum equation. So that kind of equations are being used in HEC-Ras 2D modeling, and finite difference, finite volume, they were combining to have the best opportunity to have orthogonalities or that kind of things they were using at that time. I am not going into details of that. This is gradually improving. And then similarly, mic is also another model, mic flow modeling. So there mic 0 is the basic base, like common name of DHI, which is the base. Then mic 1.1 basically 1D, and depth average basically it is in 1980 it came a one-dimensional model for river flow channel, and then Mike 2-1, that is two-dimensional, and but depth average 1 means. So the two depth average means for the entire depth you get one value of velocity. I mean it is not changing across the depth but across the width and this thing. So that's why it is 2-1 model, 1990, a two-dimensional free surface flow in river and coastal areas. So similarly Mike 3, they are now working on 3D, we are also working on 3D, quasi 3D kind of things. Mike C, a modeling tool for integrated surface, subsurface hydrological simulation. So then Mike flood, there they combine Mike 1-1 and Mike 2-1. When it is spreading, then they go for 2-1, otherwise 1-1. So that kind of things. So Mike Plus is the modern integrated platform for urban water infrastructure modeling. So that kind of things are equation wise. Again, if you see, it is in the conservative form, governing equation in the terms of Q, continuity and momentum equation. That basics remain almost same in different forms. Okay, and they were using 6-point implicit finite difference key. Okay, at that time. Now these are the unsteady when it is 2D model. Again, the similar equation form with turbulence being used here. So that is what is the equation. Then we come to the Brahma flow modeling. Okay, there is 1D and 2D approach for governing equation. That is, but today we will be dealing mostly on 2D. Our all training will be on 2D modeling. So hydrodynamic 2D modeling. So that, but then we will just briefly talk about how 1D and all those things were compared long back, and then how we are coming 2D. We are just comparing recently, and then 1D we compared long back. 2D also was compared at that time, but then I am just presenting some of the old comparison and then some of the new comparison I will be doing very quickly, and then we will be showing how Brahma model can be applied for different work. Okay, so as a history, that Brahma means, as you know, that it is the braided river aid hydromorphological analyzer. It's basically an abbreviation which is talking about, though it is braided river aid means we gave that name considering because the braided river are most complicated, but it doesn't mean that it cannot be applied to any other river. It can be applied to any river. Braided river means the term is coming because it is the most complex situation can be modeled. HEC-Ras can be also applied there. I mean, Mike or Telemech, any model can be applied. So, but then at that time we named it like that, braided river 8 hydromorphological analyzer, means morphological component is also there, that is sediment transport and all those things. So, okay. So this is the IIT Guwahat in collaboration with Brahmaputra board. We are developing that things, and of course we are getting other comments, support, reviews from CWPRS, CWC and other organizations also, other IITs also. So development history, if we talk about, then Brahma 1D and 2D, it was initially developed during 1997-1999. But it was not named as Brahma at that point, and it was not taken into a user-friendly platform. I mean, you need to run it directly the code, not in a platform kind of things. So, but it was developed at that time, 1997-1990. At that time, even Mike was not coming in 2D form, and then HEC-Ras also 2D was not coming at that time. So both one-dimensional and two-dimensional model for rivers and channel, and that was named as Brahma during 2009. Okay. Then Brahma 2D vegetation module was added because we found that most of the river we have vegetation and it has a lot of influence. It need to be modeled, so that's why we added the vegetation model there. Then we found that porcupine is one of the structure which is used in many places here, so we added that Brahma 2D porcupine model also. Then Brahma turbulence, when it comes the flow characteristic changes, so we made the Brahma turb model which is capable of simulating a flow when there is a lot of turbulence, and so that way it is gradually coming in a different form and different things are being added. So then Brahma 1D with groundwater flow coupling, that was also done. I think it was also done in 2000, I think 7, 8, I think during that period that was done. Then Brahma 1D DRFF, that is actually 1D, of course the Brahma 1D groundwater and coupling is also on 1D. And Brahma 1D, by 1D I think by that time you have done something, you understand what we mean by 1D. 1D means river is considered as one dimensional. There, whatever shape of the river is there, but ultimately what we calculate, we get a single velocity in the entire channel like this, okay? And then if it is 2D, then you will be getting this direction, that direction, different direction velocity, okay? So these are the simplification that we do. And then Brahma 1D DRFF, that is very important, that coupling with the reservoir operation model or with release information of reservoir, say reservoir is releasing some amount, and triggering of the same through cloud computing using sensor based input for better management of the reservoir and its downstream. That actually how it came, that we had several reservoirs, several dams in different places, and there always a problem arises, like downstream suddenly flood is happening and then district authority remain responsible for the downstream. Then they said always, or people also say that so and so dam company or power company has released the water, that's why the flooding. So they are safe. Dam company says that, or the power company says that we released that kind of water earlier also, but it is not causing flood, and we do not know what is the situation at downstream, say 70 kilometer downstream, whether it is raining or what is happening, that we do not know. So how can we say that it will create flood? Because similar amount of release we made before also, and that was not causing flood. So this flood is not because of this release, this flood is because of having more water at the downstream. So we thought that blame game will not solve the problem, so they approached us actually. Then we told that let us do it in a transparent way. What amount the power company is releasing, power company means I am talking about hydro company is releasing, that they will give as an input, and if they do not give it, then from rainfall also we can do the simulation and we can operation. They said they know better, we will give the input, and then they will give the input as a what amount they are releasing and how much amount of water is there at the downstream, that we can get by installing some sensors. So the sensor will give us data, and in the cloud computing it will happen. Basically in some server also you can do that. So it will compute that if this is the level, this is the amount released, and that is the amount coming from the tributaries, all sensor based, then what will be the flood level. And then warning can be given by district authority based on this model result. So that was initially funded by NEPCO, and then we are working with Brahma board also in collaboration, and that way this model is installed, and then now they can give the warning properly. Okay, but there is again some problem, practical problem, that sensor, sometimes the flood becomes so high that sensor installation itself become a problem, their sensor was washed away. That kind of practical problems are also there, but still we are trying to reduce the number of sensors which can give us optimal information about the situation. That kind of things are there, that was developed. Then Brahma 2D flood mapper. Now when the flood happens, how it will be spreading in the floodplain and how this will be inundating the area, for what kind of flood, what can happen, that we were discussing, that how can we have ML model kind of things there also. Like yes, that once the model generate this kind of things, now with other model that we have a collaboration with Netherlands also. Then we are also developing our own ML model, they are also developing their own ML model. And then the flooded area we are providing, and then we are trying to see that, suppose an administrator, he immediately want to know if this is the discharge coming in, then what will be the flood situation. So that kind of things immediately can be obtained. So we have made a 2D flood mapper. Then Brahma 2D sediment model, basically integration of sediment transport model. We use Exner sediment mass continuity equation for bed load and mass conservation equation for suspended sediment has been coupled with Brahma 2D model in order to study the river bed evolution. Okay, so then latest we are just working on, this has started, the Brahma next gen we are calling it. This is basically bridging river hydraulics, aquatic ecosystem, infrastructure risk, and art observatory, as well as AI. So that is our researcher who were working in Brahma model earlier, now in different places, of course. So they are now working on that, and we are hopeful that if it comes, it will be again one with the AI application itself. Now, equation wise, if you see, this is written in matrix form, but the same similar equation, basically Navier-Stokes equation used in the Brahma 2D equation, and then you can see the source term, there are turbulence part is also coming, and then TVD McCormack and explicit two-step predictor character scheme has been used numerically. I am not going into details of that, and it's capable of capturing shock was employed as the numerical scheme in the model. So this was adopted after a thorough comparison of implicit and explicit scheme. Actually, we are using explicit scheme only. Why? I just want to explain that if you use explicit scheme, I am not going into details, of course. I mean, just you can take that implicit scheme, of course, that in the last course I kept that, but because of time, paucity of time, I am not keeping it here. But the fact is that in basically numerical schemes, how it works, suppose you have dy dx or dv dx, I mean rate of change of velocity or rate of change of depth with respect to time or space, okay. Now, that is basically in simple term, if you think, say we were talking about change of velocity, change of discharge, change of depth with respect to space and time. So, suppose we know the velocity here, velocity there, then if we take this velocity minus that velocity divided by the distance, that will give you rate of change of velocity within that in a linear way, okay. Just this is the basis of suppose numerical scheme, any numerical scheme. But then when you take these things, dv dt is also there in time. Now if you take that this is today, but next time you do not know, because model is doing for the next time also. So in implicit scheme, we use some unknown point from the next time level, but in explicit scheme, we do not use unknown time level information, but we use only known time level information, and then from that we try to compute the next time level. Now here the difficulty is that if you make your dx and your delta t very large, or combination is not very correct, then it becomes unstable. But if you use those things small, then it will work perfectly. In implicit, as you are involving unknown things also there, so it will iterate and it will just give you the value so that both are satisfied. But in that process, there is a issue. Implicit scheme can remain stable even if because they are adjusting those values, even if there is a error introduced, okay. So we actually work on implicit and explicit scheme, and we found explicit scheme takes more time because you cannot increase your delta x or delta t, but implicit scheme can run in a short time. But finally sometimes you may get, if you are not very expert in deciding those time and this thing, then there may be erroneous result, but still it can stable, it can remain stable. So we thought that these models are generally used for deciding what should be our remedial measures, so not for directly for forecasting. For forecasting, of course, now if we do, we need a faster things. So we can develop again AI there for forecast or ML model kind of things. So, but then for deciding a best river training work, what can solve our problem? For that kind of things, say for implementation, for design, it will take several days, several months. So if we take some more time in running the model, there is no harm. I mean, if we run the model for 1 day and we get a better result, if you run the model for half day and you have a doubt about the result sometimes, then why to use that? Rather, let us use because you will see that different model, when you use different numerical scheme, results will be different. That's why even in Telemec, I have just checked one of my student work there in Germany, and then we found that in Telemec they use finite volume and finite element combination sometimes, and that also give totally different results. So people get confused that which one is correct. So with that we are using basically explicit scheme. Our model takes time, but we rely on that. Now I'm just showing you when it is in 2016, as you can see here, the 2016, it was actually first when we developed in 2000, as I told us timeline, but then 2016 we thought that this need to be validated with the actual field. So a entire Brahmaputra from, not entire Brahmaputra from Tezpur, that is from this Bhumuraguri bridge to the Pandu. From Tezpur to Pandu, we did the cross-sectional survey, okay? Not very close cross-section, but it gives fairly good idea. So we did cross-sectional survey of about 131 kilometer. So around 30 kilometer we had, around 10 kilometer or 12 kilometer we had one cross-section. And then with that cross-section, now shape itself you can see that it is quite wide, sometime then it is going, and in the Guwahati part it is quite narrow. So this is the downstream is the Guwahati part, upstream is the this one. So that kind of change in cross section is there. Now with that survey we got the actual depth, actual bathymetry, actual velocity, all were measured, and then you can see the cross section how it is changing. And most challenging is modeling in this kind of situation. Here you see at the upstream Tezpur, the width is 4,000 around, okay, that means 4 kilometer. Then it is 10,000, means 10 kilometer. Then again 10 kilometer, it is coming almost near 10 kilometer. Then it is 15 kilometer. It goes to 15 kilometer, section 6. Then it is 6 kilometer, 4 kilometer, 6 kilometer again, just at the upstream, and near Soraighat bridge it comes to what? Even 1.5 kilometer. So that way, where your bridge is, so actual river cross section is changing from, here it is from 6 kilometer to 1.5 kilometer. That I am emphasizing because these things influence. Because ultimately, entire channel we are converting it to a equivalent 1D channel, and then we need to find the appropriate value. Considering those things, we took the approach of modeling it in a different way, and then how the results comes, that was also compared. So initially, as I told, the beam and warming was the Brahma model once, again it is an implicit scheme basically, and then HEC-Ras was applied, this is 1D at that time, and then predictor corrector method, that was also we are using in Brahma. So we use different numerical scheme, and as you can see that when we give an input hydrograph like this, HEC-Ras is computing the output hydrograph at a particular output point like this. And then if you use beam and warming, that is implicit scheme, it is stable, but it is computing like that. Now we do not know whether this one is correct or this one is correct. That need a verification. But our predictor corrector explicit scheme, which is giving the value in between, and every point, only issue is that it is in a peak is coming correctly. In all those things, how much can be the high peak, that is coming correctly in all the model. And again, if it is early reaching, then it is safer for conservative in a sense that it is safer if we know that it is reaching earlier. So we did not, we just dropped this implicit and then we went to explicit, which is coming earlier, and slightly even higher peak we are getting here, which is crossing at that. So this value is obtained exactly at the same time. So considering all those things, we decided to go for this model. And then if you see that when you compare the surface or the level, water level or depth, so this red is the, it is in 2016. So HEC-Ras is the red one, this is the bathymetry, this is green is the bathymetry, and HEC-Ras is the red one, and Brahma is the blue one. Initially we got confused whether this is correct or this is, apparently it looked like that, the bathymetry shape, and this is following almost parallel, HEC-Ras one. But ours is going like this, but conceptually we thought that it should be okay because we are also using the all possible region here, all possible physical consideration. Then we thought that okay, let us collect the actual data. So we collected the discharge versus stage data that was available, and then the discharge versus stage data. With that we actually fitted the equation, and from that when we compare, then it is very interesting result we got. Brahma 1D was giving discharge, computed discharge by Brahma 1D at that point is 33,682. Discharge, though we think that in a river, suppose whatever discharge is coming, same discharge will continue, but it may not be, because there remain in channel storage, and that way discharge can change sometimes. When you are having a wider one, channel will contain some in channel discharge, and then gradually it is releasing. So that way in Brahma we got it as 33.682. It is almost close. In HEC-Ras we got it 33.540. So discharge wise, this point, end point, we are getting almost same. Then stage discharge with a lot of historical data, computed stage, first computed stage. In Brahma the computed stage is 47.86, that you can see here, that is going like this. This is a narrow channel which is actually converging from 6,000 to 1,500. So though it is slope is more, so flow is moving faster, need to move faster, but channel is also very narrow. So considering that point, here our level remains like that. And that level we got 47.86 computed. But Brahma model, HEC-Ras we got 43.90. And actual stage for this discharge from the actual data, that we got here 47.80. Then for this discharge 33.540, we got 47.30. So there is a difference between the computed stage and the computed actual stage in HEC-Ras, but our computed stage and actual stage, these are quite close. So that way also at that time 2016 itself, it was approved, the model was, but still we are refining it further and further in 2D level also. So that way this modeling approach is processing, and it is just the same thing, because your velocity is, HEC-Ras is computing more here, velocity is computed more, so your depth is coming down, and our velocity is here, this one, and that's why. Otherwise the velocity things are also almost trend wise matching. Okay. Then let us come to Brahma 2D, braided river 8, again drawing a reference to HEC-Ras and Brahma, as you will be learning both the model. So there, and it was, see, 2016 means HEC-Ras was also in 2016 at that time. Now HEC-Ras is also improving with different things. So now if you run, you may get a different results again. So this is what, that's why I am emphasizing the date. Okay. So, but now when we are running with Brahma and these things, we decided to take, we were asked that can you compare these things. Actually we were comparing earlier also, so then we thought that let us compare latest things also. So we had a bathymetric data of a very complex channel near the, our Ujan Bazar area, if you are here, in the Guwahati city itself. A lot of river training works, a lot of, these developments are coming up. What is called riverfront development activities. From the other side also a lot of things are coming up. So that's why this is quite a complex area, and we had bathymetric data surveyed for that particular reach. So we took that particular area for comparison, and we all will be happy to see the comparison, I believe. You see that this is the bathymetry, and then we made our grid in Brahma, and similar grid with the similar dimension, it was made in the HEC-Ras also. Okay, and this is the bathymetry is of course surveyed bathymetry, so same bathymetry was used, and we will have to use the same bathymetry, and it is a surveyed bathymetry. And the scales are showing that what can be the depth. So 35 is the lowest point here, and high means the side it is going high. So that way, and the grids were made, computational grids. And then the result, because we had the data for April month where the discharge was very less at that time, it was 6,000 meter cube per second in the Kachari Ghat, and that point we took, and then you can see that black line is the bed level elevation of the Brahmaputra, and recorded water surface elevation is the green point. and HEC-Ras, these are dash actually. HEC-Ras is basically the water surface elevation, and blue is the Brahma's water surface. Only in some point you can see the blue line, because both are matching perfectly. Both are matching perfectly. So I told that results will be okay. So results will be okay. As it is explicit, our time of computation is more. So at this section we found that, so we validated both the things. Similarly, in other program we have also validated with mic also, even in some point. So that way, then we validated with telemech also. There telemech was giving something erroneous result, but Brahma model was giving, for the same site we did that. Now with that, telemech was giving erroneous result, means what I say, that if you use different scheme it will give different results. So that kind of things, and in some of the point they were giving quite erroneous result. Well, so now that is what is the validation, and after that, once it is validated, we applied it for higher level also. We check that if the discharge is 25,000 meter cube per second, then whether this is giving correct result or not. Here the Brahma and HEC-Ras both are giving almost similar result, the blue and the red line. So that way we just saw that it is giving good result, and not only this is just about the depth we are talking about or the level we are talking about, but there is more important point, because that study we did, because a lot of scouring happened. Why? Because a lot of circulatory current forms, and when we calculate in design, many a time that scouring depth is calculated based on the linear normal flow conditions, and this effect of the whirlpool scouring is not considered. So one of my students has recently worked on that, and just that how we can combine this both to see which are the most potential scouring locations. So that is again important, and that's why, and then we need to understand why this scouring is happening. So that you can see that this is what is for 25,000 flow depth in Brahma model. That was, of course, I show it for one section only, but in the entire plan form, whether it is matching or not. So that part, when we went, that you can see that this range is from 0 to 14, and here also range is from 0 to 14 range wise. But our color combination is like this. We choose to give this kind of color combination because we feel that red people see means danger. So higher depth is danger. So our color is coming red here, and here of course they are using the same color from light to dark. So they are getting same thing, but otherwise it is same. Then I thought, yesterday we thought, people may again get confused seeing that one is red and these things another is, but because it is our own model, it is in our own hand, we just change the color code to the same what the Brahma is, so what the HEC-Ras is doing, and that result you can see exactly the same. When we change the color code, it is exactly the same result we are getting. So that way, I mean, we compared the depth as a whole, then we compared the flow velocity. That also you can see that again this is high, but the range again here is slightly different. It is almost similar, but here it is becoming more yellow and this kind of things, but the value wise it is same. It is also from 0 to 5, and it is also from 0 to 5, and this is. Then here also we use the same, we just change the color code, though it is apparently looking same, but it's not exactly same. So we change these things, and then we got the color combination almost similar. This is in velocity. So that way these are working fine, and this is the most complex situation. Now question is that this is depth and velocity we have compared, but where the whirlpool is happening, where these circulatory currents are forming, that also we compared. For that we need to, these are control plot, but then for that we need to plot the vector, that is direction, how the flow is actually moving. That we need to plot. So in both the model, this is HEC-Ras, where actually they are plotting they have the provision of plotting contour map with the this vector map. Okay, on the contour map itself vector is plotting, but we are plotting directly the vector map. The reason is that this gives us the opportunity to see that what exactly is there, why the color, what has made the circulatory current to form. So if we, but then this is same, 1, 2, 3, 4, these are the location, 1, 2, 3, 4, everywhere the circulatory current what we are getting is same. We take a close view now. This is in Brahma model. So here we see the Google map directly below, and then we are seeing what is happening, that this is an extended portion here in the river. So it has formed a circulatory current. This is shallower portion. So this is like that. Here also why it is forming, that we can see. Here also we can see that this is an extended portion. One channel is also coming from that side, and it is forming like this. Here also these are the 4 circulatory zone and that we have visualized. And in HEC-Ras also we have seen the same circulatory zone in different portion. Of course the background, the Google map we are not seeing because of the, it is on the contour map. Okay, so that we have just compared these things, and so I hope that this will this has rather given us also more confidence that the results are same or similar results we are working, and it will build confidence on the user also. It may take time, but then take time means computational time is more, because it is, we are using explicit scheme, relying on that, and then, but it is result wise there is no doubt, and then sometimes we get some better opportunity in different work because it is our indigenous model. Well, to what time I should go I don't know. It was given from 10 to 11:15 or something like that originally. Now it is what time? 11:05. Okay. So some of the application, particularly for you are also here, so I would like to show some of the application, but there are a lot. I don't know how much I will be able to cover. So I'll go quickly because actual application you will be doing in the rest of the class. Okay. So this is what is the already I have shown how circulatory current can be simulated. This is in Majuli, where actually we had the field data collected. We see with all field data we collected, and then this modeling was done. These are the sparse, 4 sparse were there, how it were placed, and how this circulatory current were formed. And then most important that the sparse were always eroded. So we thought of doing 3D there, because why the, you can see the velocity in the near the spar in the 3D, the high velocity occur at the bottoms. That's why the bottom part gets covered and spars fade. So that we could get, and this gave us a deep correction. That is, we made a 3D model for that, and that 3D model was also applied, and we could see that. Okay. So this is of course not in our Brahma model when we use of our own from our side, but in the user friendly form we are yet to give the 3D view, because that is not included in the user friendly form. Okay. So but then we are developing it. Then this is a case, what I will tell you, there is a tiding river in Arunachal, and this was a very critical issue, that this is in the China border, and the breeze were given there. 4 times the breeze was washed away, because suddenly high discharge come, and what should be the, how to design that or what to do, that was a confusing things. So then this was referred to us. Again there we applied Mike model also and our Brahma model. First we applied Brahma model, and you could see that high discharge or high velocity is happening, flow depth is also high, velocity is also happening very high. You can see the arrows are becoming very large, means high velocity is happening, and because there were actually breeze were constructed with some obstruction, so some piers, so velocity became very high and it eroded the things. So breeze were washed away 4 times, and this we did in 2013, I think, like that. And then we modeled it. We suggested that breeze can be given from the end to end without giving a piers, because river is not that broad. So you make your abutment strong and give you side things properly, side bank protection on that side also. So, and then you make the breeze, because with that we make in our model that if we make that, velocity reduces a lot, and that way it will stable. And with the help of God, I would always like to say, because see what flow will come, because we design it for a particular flow. say this much return period or that kind of, but then if the flow comes more than that, then we are helpless sometimes, because economy prevent us for making a very high design, okay. So, and till date this bridge is standing well, so almost 10 years has passed. So this is one example. Then implementation of Brahma 2D model. There in a water resource department we had a issue that porcupine they wanted to use because there were some erosion in this part. So we model it. This is a complex, very complex braided river, and that was model. Then this result you can see that if we use porcupine, it is without porcupine and this is with porcupine. And this is the velocity, depth control, and then this is what is your velocity direction, how it changed. This is without porcupine and this is with porcupine screen. So that way it was developed. I'll give you details later. Similarly, in Brahma 2D model in Nimati Ghat, on this side it is Majuli, there were some erosion that also we worked with Water Resource Department, Kaptabasam, and then this porcupine we implemented, and then we found that how with implementation of porcupine the velocity come down here, and that of course later we, it was published also. It is the probably good publication I will say in terms of that, that this is a academia and Water Resource Department. That's a collaborative work, and this was published ultimately. So that way it is a good work. Then this is our the main Brahma DRFF model which we are developing with NEPCO, and that we can see that how the flow is one-day model, how the hydrograph is moving after release, and this is how the flow depth can be seen in the cross section, and that actually already installed in the site. I'm not going in detail because of paucity of time. And in Brahmaputra board already you have this Nihari laboratory, large laboratory. Pune also has that kind of big laboratory. So in this we ran the Majuli situation, and then in Brahma model we ran the Majuli situation. Then we saw that there is a possibility that if a dredge channel can be made, but making of dredge channel is a questionable, that is a different point. But if we make a dredge channel, velocity can be reduced here. So that detailed study was done, and then if we make a dredge channel like this, then the flow velocity can be reduced on the Nimati Ghat. Of course later that erosion happened, and with because that channel was not made, and this is striking directly, as you can see that velocity is coming from this side. This is the Majuli side. When we push the water from there, it is striking here. So there are some porcupine screens were used, which I have already shown you later. And then as I told you, eco-hydraulic application of Brahma 2D, that in Bhugde river in Jorhat, you can see that this is how the model was applied. And what is habitat suitability? Basically, which portion is suitable for fish habitat. So that habitat suitability, we found the discharge, actually you see weighted usable area by fish, when it discharge increases, fish is it not become suitable for fish, and habitat suitability get reduced like this. So that way how much flow can be maintained and how we can have a better situation for habitat, so in the aquatic life, that we can combine, and that we have combined with Brahma model and then habitat suitability kind of things, and that work was published in American Society of Civil Engineering, Journal of Hydrologic Engineering. So that way these are some of the good things that are happening, and visualization so far is concerned, that Majuli part as I showed, that this can be seen how the flow is moving, and this is in Brahma model how you can visualize the things, okay. And then this is the same model we tried with vegetation. Well, if we put vegetation, we tried with rigid vegetation as well as flexible vegetation, and how the velocity, this is without vegetation, how the velocity is slightly high, and with vegetation how the velocity has come down. Also we have tried in curved channel like this, these are very standard curved shape, how the velocity comes down with vegetation. All those things has been done, and finally this work was also published, and then we applied this in practical field also. And then vegetation, not only just vegetation, in what pattern we are putting the vegetation. This is the square pattern, this is the interlace pattern, this is the hexagonal pattern. So how we put the vegetation, depending on that, how the velocity will reduce. That is, you can see that interlace pattern, square pattern, hexagonal pattern, all we can put in the Brahma model, and we can see that interlace pattern can reduce the velocity by 68%, hexagonal pattern by 69%, and then square pattern is slightly less. So that way, what kind of shape we need to use, that was also important, and this was also published. And then we got very good feedback from Pune, CWPRS, that GIS integration can we do. So we did the GIS integration. Now, say if we type a place here, say, then I'm just showing here, if I type this place Umananda, then it will take you to the Umananda. You may have to scroll down sometime depending on the situation, the exact position to get, but you are getting it. Rest you can put here, and then it is, you can get the position, and you can do the modeling of that part. Now question is that bathymetric survey. That is, of course, we always encourage that bathymetric survey should be done, but in case it is very difficult to do bathymetric survey in some remote area, or very hurriedly you need to have some, with less accuracy also you want to get some information, then we can download bathymetry and we can use the bathymetric data. So different bathymetric data we can download. That I will show that this is in Brahma model. We have the option here that first, if you have your own bathymetric survey, you can upload DEM and then you can get it. If you do not have, you can extract elevation. So like that you can extract the elevation, and you can see all this different cross section you are getting. And then if I just click in a particular cross section, you can get this cross section visible here, and then you can see that this is the cross section 51, that this is what, and what is that things. So that way when you have, of course it is from our actual bathymetry, but if you download, then also you will be getting. But in that you should be very careful, because when you download bathymetry or from SRTM kind of things, there what is happening, where there is a water level, that will not show the bottom part. So it will be coming like this. If there is a water here, that will go straight in this portion. So actually area of actual section will go down. That way there will be erroneous. So what we did, that this is the extracted bathymetry, as you can see, DEM data. This is showing like this. And there we have done one things to fit, that if it is coming like this, if it is, then we can fit this point, and then we have found that it is quite useful in Brahma. We have that option. That is, if you are going to the field, then to do the entire bathymetric survey, it will be quite costly also. But from the local people, if you get that even simply with a bamboo, suppose there are different channel, what is the depth of this channel, then suppose one reading if you take, you get a fairly good idea. Similarly, if you get those informations, and that information you fit into our model, from the extracted bathymetry, it will convert to a very close to the real bathymetry. Of course, the bathymetry, if it is old bathymetry, then channel may be changing. But still, what we have seen, that if the channel changes, but the total cross-sectional area remain more or less same. So for the entire Brahmaputra, actually, entire Brahmaputra means not again entire Brahmaputra, from Tezpur to Pandu we had the model. So there we had the actual bathymetry, we run the model with actual bathymetry, and we have run the model with extracted bathymetry also using our fitted bathymetry. And we have found almost same result with somewhat error of say somewhere 0.3 meter kind of thing. So that can be used readily for actual application when you are in a very hurried situation, you need the things very quickly. So integration of turbulence in Brahma model, that is, of course, turbulence portion is being added later, and I am not going in detail, but this work has also been published, and we studied there in different section how with use of turbulence we can get depth and velocity different. So that has also been done. Okay, so this work, as I said, that it is also published in ISS Journal of Hydraulic Engineering. Then integration of image processing in vegetation. Now vegetation, whether we will give rigid or flexible, that is one thing, but how we will see that what kind of obstruction is there. Now here, the vegetation, you can take photograph. If you take a photograph of vegetation, then it will just mask this portion and it will show how much is the obstructed area. And then once this is done, then you will get the effective change in resistation or the flow parameter, resistance and the flow parameter. That way vegetation, different kind of vegetation, you can take photograph going to the site and can put in the model, and that can give you the result. So here you have that vegetation present or absent first, then initial row, grid point, which point to which point you have the vegetation, initial column, set grid or flexible vegetation, rigid or flexible or mixed vegetation. If it is mixed vegetation, you have that option also. So if you put all those things and then you can put it there, and then the model will give you the result. Then porcupine, as I said, that porcupine is when you have a porcupine, then you can just take the porcupine and then you can just mention that in which section you have porcupine. We are providing 8, but we can use any more number also. We are providing the porcupine. If you provide the initial row, final row, and the column number, all these things, I mean grid wise, then it will take the porcupine. So more than 8 also you can go, but that 8 is a common, that's why we kept it there. But then with image also you can do it. Image also you can load, and then that can also do it. So that kind of things are there, and with this actually we studied that, I showed that in the Nimati Ghat, just opposite of the Majuli side, and you can see that this is what is the green line is the basically modeling with porcupine, and this is model without porcupine. This is the velocity is increasing without model, but with porcupine the velocity is coming down, and in the field it was measured by water resource department, and it is coming quite close to what our model is giving. And again there is emerge, it can be immersed, it can be submerged, so that kind of things can be also there. And this work, as I told, that it is a combination of, as you can see, that some people are from water resource department, some people are from IIT, so that way a combined study was there, and with industry, and if I call water resource department as the industry, then IIT as the academia, so we did it in combination. So that kind of things are happening, and this work was published in 2024. Similarly, that, as I told, the porcupine can be used here. Now in the same side, Guwahati nearby, on the other side actually there are some porcupine on the North Guwahati side. On the Guwahati side, the same model we have used, and we can just put the porcupine here, and then we can see how the velocity is changing. Here this is without porcupine, with porcupine how velocity got dropped, as you can see here. So that, and then how much its effect can be coming here, that also you can see effect is not that much, but we can use porcupine there up to this much. And the same porcupine we have used here, but then in here, of course in HEC-Ras, here what is the advantage, say you do not know how much velocity, how much will be the change in the resistance parameter, or how much will be the change in the porosity with the use of porcupine. But in Brahma model, you can simply put the porcupine. You can give the photo, or you can just mention that this size of porcupine. So those things will be automatically calculate how much is the resistance, and that way it will be giving you the result. How much is the change to the flow resistance, and it will give the result. But here we have used the, in HEC-Ras also we have given that resistance, but changing the resistance parameter N. In Brahma also we can do that, but in Brahma for user convenience, it is basically because any user may not be knowing what is the change value of N, but you can just put the porcupine and you can get the result. Here you need to change the N value. Now also in the latest version of HEC-Ras, they have used the permeability parameter, some of the other parameter, that also you need to know. You can put, and you can use it for different structures. So that way, I mean, we are just comparing those things. So integration of sediment transport, I am not going in detail, but then here you see several sediment transport formula you can use. Out of that, which one we need to use, that is important. And then we have compared our Brahma model sediment transport with different experimental result of different studies. It is not our model study is ours, so model prediction is the red one, and initial bed elevation is the black one, and experimental results of others, as you can see, the Sony et al., they did the experiment and their experimental results, and this is quite compared. And then here also it is another study which was compared. So that way, even for sediment transport, this model was validated well, and that work was of course published. And now we are applying it to Dibang and Siang River to do the sediment transport study. So similarly, as I told, that flood hazard model, so these are some of the equation. because of paucity of time I am not going in detail. But then for different discharges, how the flood hazard get changed. This is basically hazard. Hazard is actually a combination of velocity and depth. So that equation was there, a simple equation. So with that, actually we calculated the hazard map, and then we found that for say 200 discharge it is like that, for 2000 discharge, and 5000 it is, 10,000 it is. So how the hazard is increasing, that we can see, and then flood hazard map developed for this thing with embankment. If we put an embankment, now see here, if we remove the embankment, then what is happening? How much is the hazard? So what is the role of embankment? If you put the embankment, this part which is otherwise came as the hazard prone, now if you put the embankment, this is, if the embankment is safe, then this is safe. It is, hazard is not coming. Even in very high discharge of 10,000 cubic also, this is remaining safe. Similarly this part. So that the role of embankment, how it can save, that can be understood. At the same time, now suppose practically the embankment is there. If embankment fail, what will happen? That also we can see. So we should be cautious, we should be careful. So that kind of things also can be done. So this has been already came, and this has come in various newspaper, news article and different things. We were awarded also with our student team as well in ISS for this particular modeling work, and then this is a final achievement I would like to say, that when people say that it is good, so we in a very flooded time we went to Majuli, where we actually applied our model and design the vegetation method, that is distribution. What they are saying, if this would not have been done, then this would have eroded to far distance.
Sarma,
And that is what it is. And of course we went in a very precarious situation. We didn't have anyone with us. So we went in our team. So I had to go selfie videos because there were no what they were saying. Finally this Namaskar is the great part, that is the miserable solution we did. And then in a boat we travel, and in a small boat, big boat, all we had to explore to reach the site. So that's what we are trying, and we hope that with support of all organizations, all Indian organizations, we will be able to take this to the next level, and will be in a better position. India will be on the top of modeling. That is what is our hope. So with that, thank you very much. Again, some news articles are there. This is the team Brahma so far. So many students are there. Even Ranjit Deka also work with experimental study there. And then these are the different people. Some new people are getting joined. So that way, this is how we are working. Many are, she is in IIT Dhanbad now. She is in Alabama University. He is also in Alabama University. So he is in FREMA. So different people are working in different organizations. He is in IIT Delhi. So that way, the group is still working, though we are in different places. We are working for the cause and for having a better future for this modeling in India. Thank you very much. Thank you all. I always take the name of, acknowledge the name of all PhD research scholars who have worked with me and have somehow directly or in all not working on the modeling, but then directly or indirectly has contributed to the work. And also a lot of project staffs are there. Some names are not maybe there, but then a lot of funding agencies are also, I must acknowledge, they have helped so that we are working on this kind of work. So thank you very much. Thank you all. Thank you. Now I think as per schedule what is there, I don't know. Tea break. Okay, I have, it was supposed to be at 11:15 I think.